Hey students, let me try another video solution here. This is out of chapter 10 of your textbook, and it's again in the harder one, the university physics, the chapter 11, and it's number 98. And number 98 is a big one, a significant one. And it's a great problem because it involves quite a few principles, and I guess that's what makes it a hard one. And part of that is the angular momentum and energy, and another part of that is this rotational inertia. So I printed up a figure 10.11, which is our go-to figure, if you will, to find the rotational inertia of different objects. And I think, if I remember reading this problem right, I'm going to want to focus on this one because it says here, a bug flying horizontally at 1 meter per second. And so maybe I'll just kind of make kind of a silly looking bug and say, okay, here it is flying, and I'll have it flying to the right at 1 meter per second. And then it collides and sticks to the end of a uniform stick, hanging vertically. All right, and so we've got this stick that's hanging, and I think it crashes at the end. After the impact, yeah, so it sticks to the end of a uniform stick hanging vertically. Okay. After the impact, the stick swings out to a maximum angle of 5 degrees. All right, so maybe after the impact, I will draw the swing, and so it arcs out here, and the little bug is now stuck to it, and it angles out here. See if I can fit it in here. 5 degrees. And so I guess it's looking something like this. The bug comes along, hits the end, swings out. And of course, that swinging out is a kind of a lift. And then that turns our kinetic energy into potential energy. And then it probably falls back and rocks a little bit. Something like that. And that's this idea. And that's why I said I'm going to probably need something that looks like this, because here is the inertia, moment of inertia, or rotational inertia of a thin rod about an axis through its end. And so this m over, it didn't print real well, but that's its length squared over 3. Okay. So, but back to the problem here. 5 degrees from the vertical before rotating back. If the mass of the stick is, and then they go 10 times, they don't really give us a value, but it's 10 times that of the bug, calculate the length of the stick. Okay, so we have a collision, we have an impact, and probably the most important thing I can say is you ever come across a problem involving impacts, think momentum. Now, in the previous chapters, and where do we do impacts? Was that 9? We were doing a problem where we had translational motion. Actually, I just did a video recently where we had a bowling ball hit a bowling pin. I was helping a student with one where a bird of prey, I think it was a falcon, came down and grabbed a pigeon, and then the two kind of tumbled together. But the point is that when you see any kind of collision, any kind of impact, the thing the thing that should trigger in your brain right away is the principle of momentum. The momentum before the impact equals the momentum after the impact. And when we were doing those chapters, we were just doing what we call translational momentum. But now we have things that can rotate, and so now we have angular momentum. And so what I'm going to do is kind of make a little chart, as you've seen me do quite a few times. But in this case, I'm going to say the initial angular momentum and the final angular momentum are the same. So my focus is going to be on angular momentum, not on linear momentum. Okay, so I think before the collision might be a little bit harder than after the collision. And so because of that, why don't I write out the equation of the angular momentum after the collision? And so when I mean after, what I mean is a microsecond or even less right after the impact the bug makes. And so it hasn't had a chance to swing up yet. So it hasn't had a chance to slow down because of the effect of gravity. And so I'm going to put an I times omega. Hopefully that matches mv that we did for linear momentum. In place of m, I put the rotational inertia. In place of v for translational velocity, I put omega for angular velocity. So that is going to be representing, and I'll say final, but I don't mean final in terms of when the whole motion is done. I mean final as in after the impact. Okay, so this would be the angular speed right after the impact, but at that point the rod is still hanging straight down and it's beginning to then rotate up, and it's going to be then losing some of its rotational kinetic energy and becoming gravitational potential energy. Okay, so like I said, that's probably the easier side, and that alone's not easy. But let me jump to this side. This is the side that I gave you a couple of warnings about. It's easy to look at this picture and say, hey, the bug's just flying along. It doesn't have any angular momentum. And that's not quite true. Maybe in this video I better not get into a whole dialogue, but it would be the linear momentum times the distance away. And so it depends where you're measuring things from. And so then after the collision, since I'm measuring things from this rotational point, let me do that and make sure I'm consistent before. And so this r, this distance away, is really L, the length of that rod. And of course, then the little bug, I think you would agree, does have a mass and does then have a speed. And so, like I said, it might be a little bit challenging and odd to think about something going in a straight line having some angular momentum. But this form, not this form, but this form, I think shows it a little better that an object going in a straight line can have it. Well, like I said, I really feel like I should digress a lot into pointing out that objects going in a straight line can have some angular momentum, and then how much they have depends on what point you're calculating it about. The big key, though, is that you be consistent in both the left and right hand side. You can't calculate it relative to one spot and then another spot because, as I'm saying, it changes. So my point being that this bug does have some angular momentum, and of course, after the collision, it still has that same amount. So I would have something that looks like this. I guess I have an MVL. Once the bug hits and kind of sticks, then we would have the inertia that would be represented with two objects. One being the bug itself, and the other one being the rod. And so maybe I'll get the bug here. That's probably the easiest one. If you remember, our moment of inertia is summation of MI/RI squared. And in this case, if you think of the bug as just one object, then it just has a mass of m, and the distance that it is rotating about is the length of the rod, and so that would be just L squared. So this is the moment of inertia of just the bug. Now, the rod is a much harder one to calculate because each little section of the rod, if you imagine chopping this rod into, say, 10 pieces, you would then have to say that the mass is, 1/10 of the whole mass of the rod, each little piece, but each little piece is a bigger distance away. And by the time you added all 10 of those together, And even then, you should probably do better and cut it into 100 pieces or 1,000 pieces or an infinite number of pieces, and that's what our calculus is for. And so without actually doing the calculus, we've said in this one, we'll go ahead and let the author do the calculus for us. And so we've got this ml squared over 3 for the inertia of this rod, okay? And so I'm going to use that then. I'm not going to bother to calculate it. I'm just going to use it. So I'll just go ahead and put this little formula here. But in place of m, I'm going to write it in terms of 10. I'll write it as 10m because little m, in my case, has been the mass of this bug. And they said in the problem that the mass of the rod, where to go, it's 10 times right there. The mass of the, they call it a stick, not a rod. I should keep calling it a stick then. Okay, 10 times. And that's where I'm going to get that. Then we have the L squared, and then we have over 3. And that does allow for a little simplifying. For example, right here, we could factor out an m and then cancel it. I guess we could also factor out an L and cancel one of them. And so we're left with, say, v, the velocity of the bug, is equal to, let's see, what do I have left here? I have just an L here. And it looks like I have 10/3 of an L for the omega. And so maybe I better put those together, a 1L and a 10/3. I guess that's a common denominator of 3. So this would be 13L omega equals V. So under these conditions, I have a relationship then between the speed of the bug and then how much angular speed it's going to have after the collision. Of course, then it depends on the length of that rod. Okay? So, like I said, that's kind of the first thing that goes into my mind. Let me call that page 1. Okay. Because, as I go on here to page 2, the other thing going on is, again, this swinging up. And one of the things I said, if you find yourself having troubles doing any of this rotational motion stuff, kind of change it mentally into a translational problem, and it might give you a clue on noticing that we've already done problems like that. And then maybe that will give you the key insight on what to do for this problem. Well, for example, if I just had like a baseball in my hand and I tossed it up, I gave it some initial speed and it went to a certain height, you would say, oh, that sounds like an energy problem. And I would say I have the same thing here, that I have an initial speed. In this case, it's a rotational speed instead of a translational speed. But in this case, as it rotates, it slows down and gets to some maximum angle, some maximum height. And that's what this is doing. And so I was solving these types of problems with conservation of energy. And so I'm going to do that same thing here. So on page 2 here, I'll kind of make a little chart and look at my energy conservational principles. Okay. And again, probably want to be a little careful with what I mean by initial and final, because now I am not talking initial being before the impact of the bug like I did with angular momentum. So angular momentum, I was saying right before impact and right after impact. Now, what I'm thinking in my mind, calling initial and final, is this initial is after the impact of the bug, but before it got a chance to swing upward at all. Okay? So after impact, but no swinging yet. And final, then, is after it has completely come to a stop, that it has swung up its full 5 degrees. Okay? And so saying that initial kinetic plus initial potential is then equal to final kinetic plus final potential. again, kind of like this, tossing a baseball up in the air, you would say down here that the initial kinetic energy is the motion. And in this case, instead of using 1/2 mv squared, I'm going to use 1/2 I omega squared for the kinetic energy. Now, potential energy, I kind of have some freedom here. Maybe I'll write on the bottom of page 1 this mgh representing h representing its height from some reference point, its gravitational potential energy. And why don't I do, something along these lines, just to make my math a little bit easier. When I go to calculate the potential energy, say, of the bug, why don't I call that my reference point? And so right after impact, but before it swings, the bug would be at a height of 0. So that would be 0 potential energy for the bug if I do that. And that's why I like picking that reference point of where the bug is. The bug is at 0. Now, likewise, I can do the same thing with the rod. This is kind of make it probably a little bit harder because the center of mass of the rod, or the stick, is halfway between. And we could either use the same reference of 0 and then say the center of mass before the swing is L/2. Or we could kind of give a new reference place for that one and then let it swing up. Because ultimately, it is the difference between this side and that side. And so it's a matter of how much did it swing up. And so I'm not sure which would be less confusing for you guys, to measure everything from the same location, and therefore I would have a number for the initial potential energy of the stick because it would be half the length up, or to say that I'm going to use a different reference point for the center of mass, and it would then give me a 0 here. That would be the good thing about that choice. But it might bother you that I'm picking a different 0 for it. I'll tell you what, since I just put a 0 there, why don't I just say I'm going to do it that way. I'm going to just pick a new reference point of 0 and have a reference point for the bug and also have a reference point for the center of mass. And as long as I don't change those reference points as it swings up, it's good. I can have a reference point at a different place for the different objects. Because like I said, we're going to do the same thing on this side, and so the ultimate part of this is just the difference between the height on this side and the height on that side. So that's why it never matters when we do gravitational potential energy where we call 0, because ultimately it just depends on the increase or decrease in height. In this case, it's an increase. All right, so I'm going to go with that, and that's going to kind of make the math a little bit easier over here on the left-hand side. Again, that's what I like about it. Even though I've got 2 different reference points. Okay, now let's talk about the other half of this, after the swing. So coming back to our picture after the swing, so it swings up here 5 degrees and comes to a stop. Of course, then it'll rock back, but let's just imagine stopping up here at the top. This then would be 0 kinetic energy. And then there would be an mgh for the bug and an mgh for the rod. Now maybe I'll put bug and stick, because they're not going to go up the same amount. We'll go through some geometry here, and we'll see that there's a factor of 2 between those two heights. And of course, this is the mass of the bug, and this would be the mass of the stick. And we know that the stick has 10 times that mass. So let me fill that in, although maybe I'll doodle on this page right here and talk about heights, because if I, had a stick angling down here, and then it swings up, and for now I'll just call it theta, but that's going to be my 5 degrees to here. And if I'm calling down here 0, then this right here is the height they're talking about. And I'm just going to make a triangle out of this, because we'll call the length of the stick L. And so making this triangle means that this right here is L cosine theta. And I'm looking for height, h. And so probably the easiest way to kind of get this height h is to say, okay, if you mark from here all the way down, that's an L. And then if you subtract off this, L cosine theta, you get your height. And by the way, that same logic would work if I was looking at a point that's half the length of the rod. I would just be using L over 2 there. And so I'm going to say this is the height of the bug, and the height of the center of mass of the stick is using a different length, half the length of the whole rod. So I'll take L over 2 and then subtract L over 2 cosine theta. All right, so coming back to this page 2, I can then say, okay, I've got the mass of the bug, which I've been labeling as an m sub b times g. And then this height would be an L minus L cosine theta. And maybe I'll put another line down here. The energy, potential energy of the stick would be 10m times g. And then this would be L over 2 minus L over 2 cosine theta. And that's kind of nice here, because again, I can just drop this down to here. So this is 1/2 I omega squared. And I think you kind of see here where, well, maybe I'll just multiply these all out. MGL for the first one. MGL cosine theta for the second one. This next line would be 10 MGL over 2. Seeing that 2 changes that one to a 5. And then the same thing here, 10 times this, and I'll just go ahead and already cancel out the 2, so that's a 5. And then I got my MGL cosine theta. So that I can take this MGL and then this 5 MGL and put them together. So that's 6 MGL minus, and here's a 1 and a 5, minus 6 MGL cosine theta. And again, if you let me do a little more simplification on this side before I jump back over to here, I'll see a 6 and then an M and a G and an L in each of these terms. So this becomes 1 minus cosine theta. Okay. And of course, we know this angle is 5 degrees. I don't think we know the length of the rod or the mass. Of course, we do know G. So this is looking kind of hard here. But there's some other things on this other side that's going to cancel. And then, of course, don't forget what we did a while ago with the angular momentum here, okay? Oh yeah, that was the question, L. Calculate the length of the stick. Okay, so we're trying to find L. Oh, and we know V. I'm sorry, I totally forgot we also knew V. That was that 1 there. And so we know that is a 1. And see, then those are the two things we don't know, the L or the omega. And I think the same thing's going to happen here. Okay. But let's keep talking. Let me just move my equal sign to this side of my paper. Maybe that's too far. Okay. Because over here, I'm going to do a 1/2. And I'm going to do omega squared. But just like I did back here when I did angular momentum, I'm going to say that the rotational inertia is made out of the two pieces, one being the bug, okay, so there's the ml squared, and the other is this rod or stick, which is 10 ml squared. And again, the 10m, because that's the mass of the stick, 10 times the bug, and then the 3. And then again, we got that from this little chart here, okay? Now, maybe I'll simplify this. This is a 1/2. But as we said before, common denominator of these two is a 13. And so then this would be, 3/3. And so that 3 times that 10 makes 13. Oops, sorry, I got ahead of myself mentally. Common denominator is 3. And then multiplying both sides by 3, that top is a 13. Okay, and then that would be 13/3 ml squared times omega squared is now equal to 6 mgl 1 minus cosine theta. And so noticing that there is an m on each side, I can cancel those off. I could even cancel one of the L's off. And maybe I'll just do another line here. So this is 13/6 for the number. This is an L and this is an omega squared. And then over here I have a 6 and a G and a 1 minus cosine. And maybe now is a good time to put in the 5 degrees. And kind of the reason I say that is because these are just numbers, and I can even bring those numbers over. And so I get an equation involving just L and omega again. And I say again because remember we did in first part, we have an equation. I didn't put the 1 in here, but I'll go back and do that. And then I'll have the L and the omega. So grabbing my calculator here, why don't I do this first? 1 minus the cosine of 5 degrees. And so now times 9.8. And then times that 6. So that's that whole side right there. And as long as I have my calculator here, can you imagine moving the 6 over? So I'd go times 6. Maybe you can also imagine moving the 13. So divide by 13. And it looks like my L times omega squared is 0.103. Okay. Now, let me come back over to this one and put some numbers in here. Remember, this initial speed is 1, I believe. Let's check with the problem. Yeah, a bug flying horizontally at 1 collides. Because putting that at 1 and then moving the 3 over, and also the 13, gives me this. Gives me a statement that these two multiplied together is a 3 over a 13. So now I have my system of equations, if you will. I have an equation that has 2 unknowns and another equation that has the same 2 unknowns. And now you should be able to solve them. Couple ways we could do this. I think I'll do this. I'm going to write the L omega squared as an L times an omega times an omega. I like that because those two multiplied together is what this equation is saying. 3 over 13. And so now I just have an equation with an omega, and that's probably the bad part about doing that way is I'm not solving for L, I'm solving for omega. Of course, once I get omega, I can use it back here and get the L, and that's what I'm going to do. But I could have done a little different also, and then just had an equation with an L and solve for L. But this looked like less algebra, so I'm going to go this direction. All right, so let's see. I've got my point 103. Let me move the 13 over and the 3 underneath. And so my omega is 0.44, and it looks like it rounds up to an 8. Okay. And so then if I use that over here, so 3 over 13 equals L times this omega, 0.448. I can then get what the question asked, what is L? So I'll take that 3 and divide it by 13. And then I can imagine moving this over. So I'm going to divide by my last answer. And I'm going to get a length of 0.515. Nice. And so, ta-da! There's my length. All right. Long problem, good problem, involving rotations, which is always hard, but then using 2 of the big principles. Conservation of angular momentum, conservation of energy. All right. Hope that helps. Take care.